this project that will add up to 4 points. I believe it's going to be 4 points to the raw score, which is significant because each point is 2.5 points percentage-wise. So that's a full 10 points. Now, the average, the raw average, I believe was without anything 70, but I got to check on this because we got several very high grades, a whole bunch of high. And then we had a bunch of people that had trouble. So I'm doing this because I feel it would be in the best interest of everybody, feeling they have a fair shot at recouping some of this stuff. And this won't be an in-class thing. It'll be something you take home and work on. All right? Okay. Now let me go through the test now. And I'll put the solutions up for it. Is. All right, so the first one is problem 1. There's a frequency of 3 gigahertz. And it's normally an incident on a region right here. So we got an electric field normally incident on a region. That frequency, and the incident field is unknown, but the transmitted field is equal to 10 volts per meter. And then in this media, I'll call this 1, this 2. The first one was air. The second one has the parameters of sigma is equal to 0.01. 1 over ohm meters or Siemens per meter. Mu relative equal to 1. And epsilon relative equal to 4. And then they want, you can tell me what they want, but basically they want a bunch of information about incident and reflected power in fields. So I'm going to just list this. E incident, E transmitted, we know. E reflected, don't know. P incident, this is going to be average power. P reflected, and then P transmitted. So, first thing I have to do is, I know eta in region 1 is eta naught, and that's 120 pi ohm. Let's just specify. There's no magic here. You just put it on the board. You have to kind of know that. You're an electrical computer engineer. Next thing after that, we have to get eta in region 2, and that's equal to square root of j omega, in this case mu 0, because mu relative is 1, over sigma plus j omega epsilon relative times epsilon naught. Here epsilon relative is 4, right? Epsilon naught is 8.854 times 10 to the minus 12 farads per meter. When all is said and done on this one, it's 188.35 at an angle of about 0.429 degrees, I believe. Y'all get that? About? Right. And some people might have a slight. All right, so that's 82. Then you get the reflection coefficient. And this is the reflection coefficient, not transmission. Reflection coefficient is eta 2 minus eta 1 over eta 2 plus eta 1. And for that, you get 0.333, I believe, at about 180 degrees. 179.429. About. So then you've got to get the transmission coefficient. And I'm just going through, this is sort of this is going to be needed for every one of these kind of problems. You got to have reflection, got to have transmission coefficient. No matter what's given, you have to have that. You all with me on this? So it's just going through. Transmission coefficient, in this case, since it's normally incident, 1 plus reflection coefficient. And for this one, it's 0.666. Is that right? Yeah, because that's at 180, yeah. 0.666 at about 0.296 degrees. So now I have all those, and now it's sort of just a matter of filling in the blanks. Do y'all agree with this, class? And I'll do it right, I'll do it over here. Sorry, all these desks piled up. So, for starters, I know I have E transmitted, and E transmitted is equal to transmission coefficient times E incident. Therefore, E incident is simply equal to E transmitted over tau. You'll notice I asked for only magnitude, if you look at that. I didn't care about angle, all right, but you can get it. Can somebody just give me that so I don't have to keep on looking?
0.3.
Is that correct, class? Is that right? That small? We got an the incident field is, sorry.
Oh wait, I'm
This
sorry.
is 10, right? And this is, what is that, 0.666,
Oh,
right?
reflected field doesn't solve.
Damn, bro.
Whatever that is.
I did reflection.
Almost 0 degrees,
And that was
0.29 degrees. So what did you get for this?
No, it wouldn't have.
15?
I didn't hear.
15, and forget the angle. Do y'all agree with that?
Don't mind
It's
me.
about
What I
0.
did down here was I used. the
Now, if you have
I didn't use
questions,
the right
ask
data.
them, but I'm trying to go
It's
through
like
this
a
and get to the hard stuff. Y'all with me?
Yeah,
We got the
that's why I
incident
was like,
field. Now,
Yeah,
to
see,
get the
'cause I usually
reflected
am not there.
field,
You're supposed to
it's
be
just the
187
reflection
calculated.
coefficient times the incident field.
Damn.
And the reflection
That makes
coefficient is, what is it? 0.333, so it's a third of this, about 5 volts per meter, is that right? About 5 volts per meter. Now we've got all the field quantities, right? Now, in this one, I chose this on purpose so the angle didn't mess up your power transfer. The angle's almost nothing, right? So here, I'm gonna go ahead now, I'll do the powers right here, I'm gonna erase this part. So P incident is equal to, because it's an error, 1/2 magnitude of E incident squared over eta 1 or eta naught. Either one's acceptable. Do y'all agree with that? This is just a matter of taking the value, make sure it's magnitude. What somebody did, and I don't remember who, in either the transmitted or incident power, somehow you took only the real part, not the magnitude. Be careful, that's magnitude. Forget the angle, just take the magnitude. When you do this, this is going to be equal to 1/2, the incident field strength is 15, so it's going to be a magnitude of 15 squared over 120 pi. Can somebody give that to me? So I don't have to look it up. I know most people got this. 0.3 watts per meter squared, is that confirmed? Got that. Now P reflected, I don't need you to give me the negative sign. Whether it's there or not, I know if it's reflected, it's going in the opposite direction. Y'all follow me? So that was an assumed thing. When I look at P reflection, it's again, because it's an error, 1/2 magnitude of E, well, I'm gonna put E reflected times squared over eta naught. We've got E reflected over there, so this is gonna be what? 1/2, and it's gonna be times 5 squared over 120 pi, and anyone that's got it right. What'd you get? Y'all agree with this, class? Say it again.
0.03.
Is that, you have that? Okay. So, got that? Now, the next thing we're gonna do
Yeah, I do have that.
is get P transmitted.
I said I do.
Now, I'm gonna be very careful that I tell you exactly what I expect. On the final exam, you will see a problem like this. So, what I'm about to show you Put in your mind and don't forget to do it, all right? So here, it's equal to 1/2, right? It's the magnitude of the transmitted field squared. Y'all remember that, right? Then it's divided by the magnitude of eta 2, but we're not done yet. There's also a cosine, right, that appears here. Cosine, and this is the cosine of the angle associated with eta 2. Y'all with me on that? I'm going to remember that, seeing that. That's one of those things I went over. I really did try to stress that cosine variation, what will happen is if it's a good conductor, hint, if it's a good conductor, then this angle will be 45 degrees, which means the cosine of 45 is 1 over square root of 2. You'll follow me on that, class? So it's real important if this is lossy. I didn't make it lossy on purpose. It was just about nothing. If it's lossy, then that cosine will really have a role here. It'll drive it down. Y'all with me on that, class? So write it down for the final exam and just underscore. Baginski said this. All right, and you can take that to the bank. It'll be on. Okay, I'm trying to be clear so everybody doesn't wonder if maybe they'll see it again. You're going to see it again. Yes?
Did you say it's always 45 degrees?
No, I said if it's a very good conductor, it will be about 45 degrees. It can be anywhere from 0 to 45 degrees depending on how conductive the region is. And the reason I'm saying that is if you look at the definition here just for a second, see this? Let's assume it's worst case, pure conductor, and I have that, right? Well, I got the square root of j. J is really e to the j 90 degrees, right? Right? Or e to the j pi over 2 radians. The square root of that is e to the j 45 degrees. So the greatest possible angle, largest it could have, is going to be 45 degrees. You got that? Just remember this. Because it'll come back to bite you if you don't. Y'all see it? Did you have a question about it? Or not? I want to make sure you understand that. Okay with it? All right. Is there anything else in that one?
No.
Okay. Huh?
Yeah.
H transmitted.
All right. So how, oh, that's another, I'm glad we did this one. Yeah, forgot that. H transmitted. Well, H transmitted magnitude, right? Not, we don't care about phase in this one. Is going to be E transmitted, which is given, divided by what? Magnitude of eta 2. Correct, class? All right, and what, can you just tell me what is it? It's 10 over
60 pi.
what is it?
10 over 60 pi.
Yeah, but I mean the value.
0.053.
Yeah, that's right. And that would be amps per meter. Y'all with me? I just want magnitude. Correct, class? All right. So that was that problem in a nutshell. Most of you recognize this homework just about. Where people kind of fumble the ball, and I think it's just from nerves and stuff. They'll do things like put, instead of the reflection coefficient, they'll put transmission there and vice versa. They make what I consider just mistakes that had to do with your focus and attention. Sort of you wanted to move through quickly, but this was meant to be a problem seamless from beginning to end if you understood it. It shouldn't cause you any kind of problems. So now, next problem. By the way, congratulations.
Thank you.
Who went? Anybody besides Jacob go? Again? There's at least one other person in here that went, and I know it because they sent me, I believe they sent me an excuse. All right, next problem. Oh, this is a wave. Got an air-filled waveguide. So you got an air-filled guide, and the dimensions are A equals 3 centimeters. Oh, I'm sorry. Yeah, A equals 3 centimeters. Reading this right.
Yeah. Yeah, that's,
Give Give me the dimensions of the guide.
B equals 1 centimeter.
Thank you.
Length of 11 centimeters. Feed by 100 volts. Frequency.
So V source 100 volts, go ahead.
Frequency 8 gigahertz. And Z load is 200 ohms. Determine wavelength in the guide,
Yes.
guide impedance, and mode propagating
So
group.
that's it in the guide. That should be along the guide. And I'll explain it because technically the wavelength is the same inside and outside the gate, but along the guide is where it changes. And I'll talk to you about that. What's the next one?
ZO guide, the guide impedance and mode propagating.
It's a TE10.
Yeah.
So we'll get that. Go ahead.
Group velocity in the guide,
V group.
and
People
ZN.
make a mistake that they assume that V phase. Go ahead.
And ZN.
And yeah, the input impedance. So this was entirely the homework problem. All right, without a source impedance. That way it made it easy. And I didn't ask you for the voltage at the load, so you didn't have to do all that backtracking. It takes time, all right? So I try to make this thing smooth and seamless. If you knew what you did, you just flew through this one. First thing I'm going to do is get the wavelength in free space, or unguided. That's just C over F, right? It's air filled, correct, class? So if it's C over F, 3 times 10 to the 8th meters per second over the frequency of 8 times 10 to the 9th hertz. And what is that? Point.
0.0375.
Yeah. But that's not the end of the story. That's technically unguided. In the guide itself, it's going to be reduced by that factor K, right? So we have to get the cutoff frequencies next. Y'all follow me? So to get the cutoff frequencies for the MN mode, because it's air-filled, it's just C over 2 square root of M over A squared plus N over B squared. So that's the formula. And this is air-filled. If it wasn't air-filled, I wouldn't have C here. I'd have 1 over the square root of mu epsilon, just making that point in case something happens. All right? You with me on that? It's the velocity of electromagnetic propagation in the media inside the guide. It's the unguided velocity. So we have this, and if you do the math, FC10, I want to say it's 5 gigahertz, so it's really C over 2A. And I think it's 5 gigahertz. Can somebody just confirm that? All right, 5 gigahertz. FC20 is 10 gigahertz, right? And FC0, 1, somebody? Any? I know it's going to be larger than that. What is it,
0.15.
13? What is it?
15 gigahertz.
Is that what it is, class? Yeah, that sounds right. 15 gigahertz, right? Therefore, because it's driven at 8 gig, the only mode, it's a high-pass filter. The only mode that can propagate is the 1 You all agree with that? Everybody? So next, the thing we're going to do is simply calculate the value of K. Now, y'all follow my reasoning. First, determine what mode or modes propagate, then go for the value of K. And I use K. So K, since it's only one mode, is technically the square root of 1 minus FC, in this case 10 FC, right? Over F squared. Now, it has to be real. If you get a J something, you take the square root of something negative, you messed up. You probably flipped these things. That's my guess, right? That's probable. When you get this, you've got 5 over 8 squared, right? And then you subtract that from 1 and take the square root. Can somebody give me, it's point, I want to say 7 something.
Point,
What?
0.78.
0.78. So that makes the wavelength in the guide, or along the guide. Now, those additional 2 points in the beginning have to do with this, not stating explicitly along the guide, right? That's one of them. Divided by K, and isn't that 0.48, 0.048 class?
Yeah.
All right, that's meters. Next, we're gonna get the input impedance. Remember, this is a TE mode. Now, for TE mode, by the way, y'all realize whether you did good, bad, or indifferent, y'all realize these are just the homework problems, right? There's nothing here that you haven't seen many times before. The fact is, if you knew what you're doing, you shouldn't be puzzled. You should just be able to work through it. Hopefully not fanatically fast, but this was meant to be done in a way where if you knew what you're doing, it's clear, you'll be able to go. If you don't know things, then you're gonna spend a lot of time on things you don't know, and it really will hurt you. I mean, that's the way these things sort of work. So if you come here for ZTE, that's really Z unguided, or Z not unguided. And that's gonna be over K, because it's a TE mode, right? Y'all agree with that? Everybody follow me on that class? Well, Z unguided is filled with air, so it's 120 pi. So this is 120 pi ohms over K, which is equal to 0.078, or 0.78, pardon me. And what is that exact? I think it's
482.9.
482? All right. Now, next is V in the guide. That's the velocity along the guide. People assume that was phase velocity. Some people. Most of you got this right. Since it's group velocity, it's the velocity of energy travels, it's simply equal to C times K, or 3 times 10 to the 8th meters per second, right? Times K, or 0.78. And what do you get for that? 2.3 or something like that?
2.3 times 10 to the 8.
2.34 about. Okay. Now the input impedance. This is the one thing I warned you about, making sure you didn't make the mistake of degrees, or anything like that, put everything in regular. So Zn in this case, and I give you the formula, will be equal to characteristic impedance of the guide, and I'll just put TE here, times the load impedance plus J times Z naught TE times the tangent of beta in the guide times the length of the guide over Z naught TE plus J ZL times the tangent of beta in the guide times L. All right. Now, what is beta unguided? Well, it's omega over C, right? Because it's air. Y'all agree with that? I mean, some of you, because it's lossless, put down omega square root of mu epsilon. That's fine. Mu epsilon, square root of mu epsilon is 1 over C. No matter how you do this problem, you're going to get the same value of beta unguided. Y'all with me? It's not beta guided though, right? To get the guide, what do we do? Multiply by K, don't we, class? Y'all with me on that one? Remember that? Because that's the big change, right? So beta in the guide is K times omega over C. And what do you get for that? Somebody's got it right.
130.79.
130.79 radians per meter, right?
Yes, sir.
130.79, and that's radians per meter. All right. Now, that's the value that goes in here, and in your calculations, now it's per meter, and I think it's 11 centimeters long, so that's 0.11 meters. Y'all with me? This calculation becomes the make or break right there. So you need the right value of beta G, which is there. Then you need the right value of L, which is going to be in meters, because this is radians per meter, so it's got to be times meters to get radians, which is 0.11. Then you've got to take the tangent in radians. Do y'all follow me on that? Now I think, though I didn't confirm it with a lot of people, there was a mistake where they did tan in degrees, which will give you an erroneous answer, all right? So please make sure you don't do that again. I'm trying to be clear about this. That is a mistake that happens, and it will really clog you. You've got to make sure this operation is done in radians. If beta is radians per meter, and L is meters. Got me on that? All right, can you just, I want to say it's 1,000, that's what I was trying to. It's about 1,000, is it 1190 or something? Or, sorry, it's about 1,000 ohms, and it should be. It's close. You're gonna get like, I think 980 or something with a little angle, and that's just the wiggle room right here because it depends on the level of accuracy. So anything about 1,000, you got credit for, okay? And that's it. And that's in a nutshell. I didn't even worry about the angle on that because it's gonna vary some. So that's I think that was it, was it? Okay. Now, any questions before I move on? Okay. 3. All right, for the third one. You give me specs on this, but this is the old, I got a radar here, right? And I got a target. This says across, is it 5 meters squared? All right, it's at a range R equal to 10,000 meters, I believe. This has a gain of 30 dB. So far, so good. It transmits the power of watts.
500.
500 watts? 500 watts, right? And now, it's got a little antenna on top of it. Halfway dipole on top there, right? So we go through the actual question.
Radiation resistance of 200 ohms.
Yeah, RF equal 200 ohms. That's just the real part of the antenna impedance, right, class? So, anyway, let's go through this. So the first thing I asked for is what?
Power density of the target.
So I want P incident, right, at the target. Well, and I hope you methodically go through this in your mind. Start with the total power transmitted. Then assume it's isotropically distributed. So that's the smallest amount of power density you can have on a target. Then you multiply it by the gain and direction of the target. In this case, it is the full 30 dB, right? And 30 dB is equal to 10 times the log of the gain linearly, right? So it's really 3 equals log base 10 of G, or G is 10 to the third, or 1,000. I'm making sure you see that. So this is times that gain, or just times 10 to the third. That would be the power density on the target. Do y'all agree with that? Everybody with me? So just give me that value. Any?
4 times 10 to the negative 4.
4 times 10 to the minus 4. The units are watts per meter squared, right? I don't differentiate average from peak. This is just the power based on the transmit. That's all you have to worry about. Now after that, what's the next thing?
Reflected power density at the transmitter.
All right, so this is the one I think people had trouble with. Now, understand the question. The radar sends out a beam, you might say. It hits, and now some is reflected back, and there will be a power density comes back on that radar. Y'all follow me? So this is the echo return. So to get that, you take this. I'm going to say P incident here on the radar. I'm going to take P incident on the target, right? And then I'm going to multiply that by sigma. This tells me how much power is going to be scattered, right? The bigger sigma is, the more power. So I multiply it by sigma. Now that's the total amount of power scattered. But that power falls off just like an isotropic power source. It'll fall off as 1/4πr². Y'all with me? Some people went right to the radar range equation. I prefer doing it this way until you're real settled with that. So this is just going to be times 1/4πr². And that's going to be the incident power density in watts per meter squared back at the target. Can you give that to me, or anybody give it to me? Got it? I know a whole lot of people got it right. What is it?
1.58 times 10 to the negative 12.
And that would be watts per meter squared. Y'all with me? I'll put the solutions up, but I want to make sure you see how I'm getting that stuff. Y'all with me on that? That's the power density. What's the next part?
Received power.
Now, to get received power, this is in watts. So P received is in watts. And that's always going to be that right there. P incident at the radar. And then, think about it, that's watts per meter squared, so it's got to be times the area of the antenna it's hitting, the electrical area. You with me, everyone? And that's going to be lambda squared over 4 pi times the gain of the receiver. It's monostatic, they're the same. Unless there's somebody specifies something where gain of transmitter is different than gain of receiver, you assume the two are the same always, okay? Here, I need lambda before I can do that. So lambda is going to be C over F. And for this one, what's the frequency? 2 gigahertz. So this is going to be 3 times 10 to the 8 divided by 2 times 10 to the 9, or 0.15 meters. Correct, class? So now, here's what some people did. All right, they took lambda over 4 pi and squared the quantity. It's lambda squared over 4 pi, all right? The reason they did that is they were thinking Friese. Friese is this. P received, it's for 2 antennas. We have antenna 1 here, and we have antenna 2 here. And you want to know how much power is received at antenna 2. Well, Friese says P received over P transmitted, or P radiated, is going to be what? Lambda over 4 pi r squared, gain transmitter, gain receiver. So some people mistakenly used that type of a formulation. Y'all with me on this? Please make sure in your head, if you do it this way, you won't make that mistake, in my opinion. But when you're looking for a formula that just gets you the end result, sometimes you'll get confused. And you'll do things like this routinely under pressure if you're not careful. All right, so that would be the correct equation, correct, class? And for P received, some of you use the radar range equation. I'll just put it down there. P received here is P transmitted. And then you put lambda squared sigma gain transmitter, gain receiver, over 4 pi cubed r to the 4th. That'll work also. But I was trying to do it so you didn't have to write that whole thing down. You did it sequentially, right? You got each term. What do you get for this? Somebody's got it right. I did it. Does somebody have this right here? Or this that's got it right? Can you give that to me? What do you got?
2.83 times 10 to the 12.
83 times 10 to what?
Negative 12.
Minus 12 watts. That sounds right. Yeah. Then you can get it that way or this way. They'll give you the same answer. With me? Okay. Got that? What's next? Now I say I got a half-wave dipole on the actual target, and I want to know what is the maximum power received. So this is that little dipole thing. You can use Friese for this if you want. I got a little dipole here, it's a half-wave dipole, right? And I wanna know how much power is received. So this problem boils down to the two antenna problem. Really, if we look at this transmitter here, and then I got a half-wave dipole, and I wanna know how much power is received. Now, please watch this, because this one, people, only about half the people got this right. If you think about it, this is the transmitter, right? It's transmitting 500 watts. R is 10,000 meters. And now we're gonna go through and use Freeze over there. We can use Freeze to get it straight, okay? Y'all with me on that? So I can say, while you think about this one, I'll put it up here. P received, this is the maximum power, not the available power below. P received is gonna be P transmitted. Well, yeah, I'll put it this way, it's gonna be P transmitted times, and then lambda over 4 pi R squared. Gain of transmitter is 10 to the third, gain of receiver is 1.64, right? For a half-wave dipole class? Y'all with me? The directivity and gain are interchangeable unless efficiency is specified. I didn't focus on this. I gave you just, you would assume the gain. Now, this will give you, since I got P transmitted as 500, you could actually take the power density there and just multiply it by the aperture. That'll get you that too, because we know the power density at the target, right? And the aperture is just lambda squared over 4 pi times 1.64, so you can get it that way too. This way will get it. And what do you get for this? I know a lot of people got this right. Well, this is P incident target. I'm going to take this approach. Do y'all agree that's the power incident to the target, the density, right? So I can say this is 4 times 10 to the minus 4th watts per meter squared. And then the size, the electrical size of that half-wave dipole will be lambda squared over 4 pi times the gain, or 1.64. We can do it this way. Can you just give me that? Lambda is what? 0.15, so 0.15 squared over 4 pi times 4 times 10 to the minus 4 times 1.64. Anyway. People got that right. I know they did a bunch of people. I'm just.
What's lambda squared? I'll type it in. Or what's
Say again?
lambda? What's lambda?
0.15.
What's this 1.5? It's 2 gigahertz. This one, you're getting a hard.
Point, wait, 1, 2, 3, 4, 5. 1 times 10 to the negative 6?
Is that about right, class?
That's what
Yeah. And that'd be watts. Now that's P received. Then I asked for the open circuit voltage, correct? Now you're going to use that P received to get it. So V open circuit, and here's where I give you latitude. If you got that right, if you got that right, then V open circuit is simply the P received for that lambda over 2 dipole times 4 times the radiation resistance of the dipole. And here's where, if you got something marked off, and this is, if you had the right P received there, and you used 400, or you used 200 here because it said 200, you should have full credit. If you don't, come see me afterwards and I'll make it right. But this radiation resistance really for a half-wave dipole is 73.2 ohms, right? You all with me, class? So if you use that, you get full credit, but the key is getting this right there, because that was from the prior step. Agreed, class? Now, know this pretty well, this type of a problem, because you'll see it over and over again. Yeah,
Can you repeat the formula there for
which one?
What is the full record?
The open circuit, it's the square root of P received times 4 times the radiation resistance of the antenna where the power is being received at. Okay?
So why did you write RRAD was 200 if?
I put that down there because I was gonna ask some additional information at the antenna, but I did, now if you use that there and you use the red P, then I'll give you full credit, because that, I can understand that. So you're gonna get full credit if you use either that or 73.2, either one, okay? But you need to have that receive power right, okay? On the end, on the actual target. You all with me, class? And what I did, by this time a lot of you, you're already guessing. I literally take the homework or quizzes and I just modify. That's all I'm doing. I don't know if this was, I think it was a quiz, but I'm not, quiz or homework we did. I think it was a quiz. Okay. Was there Doppler on that one or not? No, that's the next one, right?
Do you have the right answer for VOP survey?
Yeah, what's the final?
Oh, I do. I'll post that. I actually, my solutions are on this. I can give that to you, but I'll tell you exactly what you're doing. That's the P received. We have,
The 10 to the minus 6.
yes.
Yeah, that you erased.
Times 4
It
times,
was-
all right.
I
If
think
you
it
use
was 1 to
200,
the
you got
minus
credit,
6.
or 73.2, you got full credit.
I think that's 1 to the
What did you
minus
get?
6.
Yeah.
You said 10 to the minus 6, but I think it was 1, like you wrote that on the board.
No, it's 1.17 times 10 to the minus 6 was the receipt.
Oh, I didn't get that all the way.
About 1.1 something, yeah, I remember that.
did.
I'll post
It
these
just,
things, all
wait,
right?
he just, oh, was he calculating that? I'm lost, I'm
This is what
sorry.
I got for open
you're
circuit when I
right.
just.
Okay,
This is the open circuit I just calculated.
on doing the V open circuit?
Yep.
Oh, okay, I wasn't doing that. I was a step ahead
Got one
or
more.
before. It's 12:51.
All right, well, for the last part, I'll put it up, but I might as well just tell you, this is, how if I try to work through it? You gotta go, you gotta go. Try to keep this thing in a hurry. For the last problem, you got a freak.
I didn't do it with
Problem 5. Halfway dipole, right here. And it's connected to 50 volts, right? 50 volts, I think most people got this right. Got a range of 2 kilometers. Here's a target.
Oh, you got a Doppler on that. I couldn't remember that one for the life of me. The
Let's
Doppler
see.
equation? For the life of me, couldn't remember it.
All right, for this one, it's current. Current is simply going to be equal to 50 over Z antenna, and that's 73.2 plus J 42.5.
0.59.
Yeah. 0.5 07 amps. After that, P radiated, or well, after that, depends what you want. Yeah, I gave you the equation for the electric field, didn't I? Yeah, you can go right for the electric field and say the magnitude of the electric field is going to be just 60 on over R right here, and you'll get the right answer. You can get rid of everything else, and that's going to be,
Just left in the J.
Okay, cool, thank you.
That's my notes.
Okay.
Zero point 0.0172 volts per meter. Y'all get that, class? Then after that, the actual incident power here, or I'm sorry, average power density There's just gonna be 1/2 magnitude of that E field squared over eta. And eta is 120 pi, and that's 4.16 times 10 to the minus 7. And then for the Doppler frequency, that Doppler is just 2 times V over the wavelength. So it's 2 times V,
4,000.
yeah, 2 times 4,000 over the wavelength, which is C over F, 3 times 10 to the 8th. And F is 2 gigahertz, right? So that would be the Doppler shift that I,
F was 1 gigahertz.
huh?
F is 1 gigahertz.
1 gigahertz?
Yep.
Just depends on that, so. And that comes down to 26,667.
Yeah.
And that was it.
Nice.
So I will send you something about the project, I don't have time to go through it, and I will, remember, you're gonna have 2 points to your raw score, and you got, I think it's up to, it's either 4 or 6 points that you're gonna get on this project that'll be added to your raw score. So take your raw score, and in your mind, add either 6 or add 8, and see where you stand, all right? Now, it's gonna put the average fairly high in this class, but